Alrighty. So let's see. Howdy. We've got some homeworks. 3, 4, 6, 7, 8. Okay, let me do something here. I presume people have downloaded the new note that was posted for today's class. So is anyone here today who doesn't have the notes for semi-definite programming? Okay, so you can look on with someone. Okay, I mean, these are my overheads that I may or may not use. You're welcome to use these until I need them or something. Okay, fine. All right. So, all right, let me first make some announcements. So you have. So let me ask you, who here attended recitation on Friday? Okay, so and Andrew was there giving recitation and everything. Okay, good. All right. So let me just get you oriented. I think this is now the last 2 weeks of classes. Is that right? It's just this week and next week. And so here's the deal. Okay. We're going to have one more homework. But for those of you who are really hopeful, you might have thought I would have assigned problem 5, which happens to be identical to problem 2, which happens to be the same as this one you've already done already. So that's why I didn't assign it. So we're going to spend today, Thursday, and next Tuesday on semi-definite optimization. Okay? And then next Thursday, I'm not exactly sure what we're going to do. And I haven't figured that out yet, but I will tell you this. Okay? I won't be here. Okay? So I actually have a conference I have to attend, and I don't usually like to miss the last class of the semester. But I am looking for an appropriate substitute. And for that matter, so I'm going to be talking to Andrew Menard about him giving the last lecture in the class. But I know this is an absurd thing. I don't know if did any of you read Tom Sawyer when you were young? Yes. Okay. So for those of you that have read it, sort of, if anybody is really interested in giving the last lecture, please talk to me or send me an email. Okay. So if you would like to get practice teaching, we can talk about your giving the last lecture in the course, which is, I'm not exactly sure what we're going to do. We may wind up not having the lecture. So I have to be at a conference. I know this breaks you all up. What can I do? Okay. Any questions on anything at this point? All right, so now let me ask you all something. Who here has heard of semi-definite optimization? Okay, in what context? Kate? Try it.
Maybe portfolio.
Okay, maybe, yeah.
More just in the OR Center. Just people talking.
More just people talking about it over at the OR Center. Okay, Jan.
In control and machine learning.
Good. Control and in...
Machine learning.
I don't...
Kernel-based bits.
Oh, yeah. Okay, I don't know too much about that. And I know next to nothing about control, but I know semi-definite programming is used extensively in control. Okay, who else had their hands raised? Okay, Pamela.
Well, we did linear programming last semester.
Last semester it was mentioned.
Yeah.
Okay.
We did a little bit about this.
Okay, and who else had their hand up? Ashish.
Machine learning.
Machine learning. Machine learning, not like pattern classification, right? Other stuff, though.
Yeah, I mean, related to the current weight series.
Okay.
And also inferring the marginals. of a large graphical model.
Marginal distributions?
Yeah, marginal distribution.
Okay, yeah, this is stuff. All right. So here's the deal, okay? So semi-definite programming, commonly known as SDP, okay, or I like to call it SDO, okay, because I want to get the word programming out of optimization. Okay, that is, I mean, George Dantzig, right? George Dantzig invented linear programming in 1947, and the name linear program was suggested to him. I forget. I was just reading this last weekend, actually, or 2 weekends ago. So it was suggested to him by a colleague, and in fact, the title of his first talk was called Programming in a Linear Structure. Now, you got to go back to 1947. Okay, there were like 3 computers in the world at that point. And the notion, in fact, it was von Neumann who had, in fact, suggested the idea that computers be designed with the notion of you give it a program and it runs that program, as opposed to building a computer just to do artillery trajectories or a computer just to invert matrices, if you see what I'm saying. Okay? And so for the longest time, program literally meant, you know, evening television program, okay, which is not software, but is a schedule or a way to conduct business. Well, these days, when we think program, we think software. And so, you know, I tell people I do work in linear programming, and they think, oh, you write software. And I tell them, well, I write software in theory. All right. So that is why, for example, the textbook by Bertsimas and Tsitsiklis is called Introduction to Linear Optimization. So we're trying to move the jargon away from programming, get the word programming out. But it's a little hard because it is. All right, so let's review LP. Okay, so watch this. So I'm going to write LP in a different way. I'm going to write C dot X and then AI dot X equals BI and X in Rn plus. Okay, so what does this mean? So where am I? I'm on page 2 of the notes. All right, so just listen to me, actually. So this says linear programming is minimize over a vector, over my vector of variables x, some linear function, subject to the fact that my x variables have to satisfy m different linear equations, okay? And my vector x has to sit in this particular cone, the non-negative orthant. And now we've learned some conic duality theory, so you recognize this instantly as just a particular cone. Okay? So that's my linear programming primal. And then I could write my dual as maximize the sum of the BI-YI's. And this is just same old, this is B transpose Y, but I really want to emphasize, think I've got multipliers on each of these equations, and I want to maximize the sum of the multipliers times the right-hand sides of the equations, subject to, and now watch this, then I'm going to have YI-AI, and I want you to think of, I've got multipliers times these vectors. I'm taking a weighted sum with positive or negative weights, okay, that has to be less than or equal to my objective function. This is just A transpose Y less than or equal to C stated differently. Okay? Or let's do it this way. Let me just take this in a sense and rearrange it and say C minus the sum of the YI AI has to lie in Rn plus. Okay? Everybody see that? And in fact, this is not Rn plus. What is it really? Anybody know what I'm getting at? Waleed. All right, it's Rn plus dual, which of course, the dual of the non-negative orthant is the non-negative orthant. Okay? So that's LP. So semi-definite programming, when did semi-definite programming come along? Well, somebody probably defined it in the 60s, okay? And it was an object of, it occasionally came up in the 70s and the 80s in some deep theoretical paper from time to time. I know one paper by Latsi Lovas. How many have heard of Lovas? No? None of you. Okay. Well, I'm glad to know more of you know my name than his name. So he's a famous computer scientist, does work in discrete optimization, and never heard of the Lovas theta function in graph theory? No? Okay. So Latsi Lovas showed that, in fact, a certain object in combinatorial optimization on graphs was related to certain optimization problem involving semi-definite matrices. And that, in fact, was a convex optimization problem, and so there was a little bit of theory that could be applied to it. But semi-definite programming really sort of hit center stage in the early 90s, so about 10 or 11 years ago, with the simultaneously happening of two events. One was a publication of a book by two Russians, Nesterov and Nemirovsky, called Polynomial Time Convex Optimization, or Polynomial Time Interior Point Methods for Convex Optimization, and then a PhD student named Fareed Alizadeh at the University of Minnesota also reinvented semi-definite optimization. And semi-definite optimization is important, I would say, and is of great interest for many of the following reasons, it turns out. It's got applications in at least three very different arenas. So one is in control theory, as, who was the one who pointed out control theory? Jan. Okay. It has all these applications in control theory, and please don't ask me what they are, okay, because I do not really understand control theory. For that, you have to talk to Jan. And it has applications in discrete optimization, integer programming, okay, of all things, all right? And it has enormous applications in convex optimization. And it is a unifying model that may overtake linear programming as the basic model for which we think about optimization, okay? But none of these things would make it really interesting if we didn't have really good algorithms for it, or I would say a really good algorithm for it. Namely, it turns out all that interior point machinery that you learned first from Andrew and then from me for linear programming almost extends exactly, literally all you have to do is take your LaTeX file and substitute this symbol for that symbol and this symbol for another symbol, and almost all the proofs go through. Okay, we will sort of see that. Okay, and in fact, I would say in the mid-90s, the excitement was so great. People thought, oh, great, we're just going to be able to solve all these problems just as easily as we solve linear programs, and that's not borne out in practice. So it turns out semi-definite programming problems are harder to solve than linear programs. But that's sort of like saying, you know, that sorting a bunch of numbers is harder than just computing the square root of 2 to 10 digits of accuracy, which takes a nanosecond. So just because it's harder than linear programming, it's still relatively very easy. All right. So what is SDP? So let's write down. So let's just, I want to review some facts and make sure you've done your homework, in a sense, literally. Okay. That let's think about this positive semi-definite cone. So we'll say sort of S n by n plus. These are going to be the set of all matrices that are symmetric and positive semi-definite. Okay? And you had to prove in your homework, how many of you were able to prove the exercise that the dual of this cone was itself? Okay. How many of you tried and failed at that? Oh, come on. You could. Somebody raise your hand. Walid, or Ashish, you were not able to do it. Okay, fine. All right. So, all right. But you know this is a closed convex cone. All right. Give me two symmetric positive semi-definite matrices. take any non-negative combination of them, they're going to be a symmetric positive semi-definite matrix. Okay? All right. So, and now we're going to be thinking of these x's as the variables. Okay? And so, I mean, literally, I remember sitting down on a summer afternoon trying to teach myself semi-definite programming, and I had to sort of shift gears so that now when I write down an x, I want you to, with a capital letter, I want you to think about it whichever way is going to be convenient for you, but let me suggest 3 different ways. Okay, one is x is a matrix. So you can think in your brain it's some n by n matrix. Okay? If you want to, though, think of it as, if you want to think that variables are really vectors or arrays of coefficients, you can think of this as an n squared long array of coefficients. Right? So it's just, you know, the first, you can sort of, in your brain, concatenate. I got the first row, and then the second row, and then the third. So if you want to, you can think of this as a vector. Okay? A vector of coefficients. Or you can think of it a third way as just an object in a space. So, right, that is, any x is in the vector space of, is in the, in a sense, vector space of real n by n matrices. In fact, actually, it's in the vector subspace of real n by n symmetric matrices. All right? So sometimes thinking of it as just an abstract object. I kid you not, sometimes when I need to sort of think of things as being non-concrete and sitting in abstract vector spaces, I think of these abstract vector spaces as sort of corresponding to disreality. Like I take a chair and I can add a chair to it and I get another chair. Something like that. In other words, so I know I can't picture it. Okay? So you can think of it in any of those 3 ways, whichever is going to be most convenient for you at the moment. I also want to remind you of another fact, okay? That if x is positive semi-definite and xi, one of the diagonal entries is 0, okay, what do I know about some of the other entries in this matrix? Okay, so just think about this for a minute. I have a matrix that's positive semi-definite, and somewhere along the diagonal, I got a 0. What must also be true? Everything in this row and this column must be 0. Okay, why is that true? Why is that true? Well, watch this. Suppose I have a non-zero entry here. So just, I'll call it A. So I have an A somewhere else. Okay? And because it's symmetric, I have to have an A over here in the same place. Okay? And then, well, what's the entry here going to be? Well, actually, let me ask you this. What must the sign of all the diagonal entries be if I'm positive semi-definite? It's going to have to be non-negative, because if I have a negative entry, if I have a -1 here, I could just hit this from the I could sort of think of my x transpose x as just lining up here and here. I could just hit everything with zeros except a 1 here and a 1 here, and I get a -1. So clearly my diagonal entries have to be non-negative. So suppose this is a 0. Well, then I hit this with 1 minus 1, 1 minus 1. And zeros everywhere else, and this is going to evaluate to, 1 minus A. And 1 minus A. Yeah, so then this is going to evaluate to 1 times 1 times 0, A squared times 0. This is going to be minus A squared, minus 2A squared, which is going to be a negative number. So clearly I can't have a 0 here. So if I don't have a 0 here, I have something positive. I don't really care what it is. I might as well just call it a 1. Okay, but if I make it a 1, then I can get this to evaluate negative. Actually, let's make it an epsilon. Then I make this a 1 and minus. Boy, now I'm blanking on you, ladies and gentlemen. I'm sorry. Who can help me out here?
something larger than minus epsilon over A or smaller than minus.
Thank you. So minus epsilon over, yes, minus epsilon over A, 1, 1, minus epsilon. So it's larger than that in magnitude.
Larger than magnitude.
Minus 2 epsilon over A. What's that going to evaluate to? I'm going to get an epsilon. Ah, yes, that's good. So I get an epsilon here, and then I get a minus 2 epsilon here, and I get another minus 2 epsilon here, and I get a 0 here. And this all evaluates to minus 3 epsilon, and that's negative. Okay, so if I have a 0 here, I've got to have zeros everywhere else. All right, just remember that fact. So now let me write down a semi-definite optimization problem in the primal form. Okay? Oh no, sorry, I've got to do one other thing before we get there, which is if x is my variable, what's a linear function of x? So here, c dot x, which is just the sum of the cj xj's, is my linear function of x. So what's a linear function of x going to be when x is a matrix? You tell me from the homework. Ashish.
I was going to ask you to repeat that again.
Sure. Ashish. No. Okay. So that is, if my variable is the matrix X, what's a linear function of my variable going to be? You understand the question? Okay. So watch. So Ashish, if my variable is a vector, is a 5-dimensional vector, okay, what's a linear function of this look like? It's like going to be some c1x1 plus.
C transpose into X.
Huh?
C transpose into X is C the vector.
Yeah, that's right. That we know that to be C transpose X, and C transpose X you can think of as defined to be c1x1 plus dot 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 c5x5. Okay, but now what's it going to look like if X is a matrix?
The way we define the dot product.
Right, the way we define the dot product in the homework. Right, and you got that question. Okay, did anybody not get that question? Right, that was very straightforward. It was just basic arithmetic. You know, so that is, right, if I have the trace of a matrix is just the sum I equals 1 to n m sub I. That's just the sum of the diagonal entries of a matrix. And then we define c dot x to be the trace, well, actually, sorry, we define it to be the sum I equals 1 to n, j equals 1 to n, cij, xij. So that is, if I have, that's going to be my linear function of x. It's going to take another matrix. We're going to take another matrix, and each of its entries is going to be the corresponding coefficient that I'm going to use to multiply that entry of x. Everybody with me? Okay. But right, you're used to thinking Cx is just the matrix product of C and x. Okay, and we get another matrix. I don't want to get a matrix. I want to get a scalar. And so I'm going to define C dot x to be, take these two matrices and just literally multiply them component-wise and add everything up. Okay? And that happens to correspond to the trace of C transpose X. Okay, that's what you proved in the homework. Okay, so that's a convenient representation because the trace has a particularly nice properties that are, it just makes everything convenient. It's just going to make proofs nice and convenient. So I want you to think, again, sort of two ways about this. One is C dot x is just the sum component-wise, Cij, Xij over all I and j. And the other is it's the trace of C transpose X. Okay? That's that. So with that in mind, I'm going to write down my, let's see, what's the notation I use? SDP. You can think of that as semi-definite primal problem is minimize, and I got x as a matrix, C dot x, subject to, well, now I've got, just like in LP, I have a linear function here, and then my x variable has to satisfy m different equations. Okay? And so these are the m different equations. Okay? And I've got the additional condition that x has to sit in this particular cone, the semi-definite cone. Okay? So that's my semi-definite programming primal problem. Okay? So let's see an example of this. And now again, so the example starts on the bottom of page 6. And let me lower the screen to do this. Whoops. Oh no. Good. Good. So in the example, I'm going to do a 3 by where x is 3 by 3. So here, for example, is my C matrix. And by the way, notice all of these matrices that are used to define things are themselves symmetric. And that's with no loss of generality. Because if I have a matrix C used to define C dot x, that winds up being the same as, so that is, C dot x is the same as 1/2 C plus 1/2 C transpose dot x. So I might as well just limit myself. So, and this is a symmetric matrix. So there's no loss of generality in just working with symmetric matrices. Okay. There's also a deeper theory that sort of says if you think of, so I'm now going to say something, and those of you that get this, fine. And those of you that don't get this, don't worry. So think of it, watch this. So if I have a vector x in Rn, okay, I can think of what is the space of all linear functions? Well, the space of all linear functions are all vectors C that are also in Rn. Okay? And more generally, if I could think of the space of all symmetric matrices abstractly is not in Rn squared because it's symmetric matrices. It's in R n times n plus 1 over 2, which is all the coefficients of the diagonal and everything above, for example. Okay? So its space of linear functions on it should be in the same dimension. Okay, so that's one way of thinking about it at an abstract level. If you don't want to get that, just get this, that I can replace any linear function by its symmetric counterpart. Okay? So here I've got A1 is this, A2 is this, and C is that. Okay. My vector of variables is just going to be this 3 by 3 matrix. And again, if you really want to, you could think of this 3 by 3 matrix as actually being a 6-dimensional vector. Because it's the objects that I need to know it are x11, 22, 33, 12, 23, and 13. Right? The guys below the diagonal are automatically then determined. Okay? And so C dot x is going to be, if I take that matrix C from the previous page, which I can do more easily than you can, I'm just going to put it right down here. Right, it's going to be 1 times x11 plus 2x12 plus 2x21. That's going to be 4x12 or 4x21. Doesn't really matter. And so by the time I'm done, C dot x is just this function of the 6 variables, of those 6, not 9 variables. Everybody with me here? Okay? And so that's my objective function. And then my A1 matrix, and, oh, sorry, the other data that I had here, yes, I wanted my right-hand side B sub 1 to be 11, and B sub 2 to be 19. And so by the time I plug in that A1 matrix and A2 matrix, I get two different equations here. And I also need the condition that this matrix be positive semi-definite. Quick question for you. Why is this not a linear program? What makes it different than a linear program? Okay?
The constraint that x is positive definite, it's constrained on the eigenvalues of.
Yeah, that is, this is far more complicated an object or constraint than that the coefficients be non-negative. Okay, that's right. That's all there is to it. Okay, so I just comment down here. It looks remarkably similar to an LP, and I want you to one way to you can think of it's just got to sit in this cone. The other way you can think of it is instead of all the variables having to be non-negative like they are in LP, you can think of all the eigenvalues have to be non-negative. Now let me suggest a way to not think about it. Okay? A way to not think about it, even though it's valid, is to say the smallest eigenvalue of this has to be non-negative. Right? If the smallest eigenvalue of this is non-negative, then everything's going to be non-negative. So so I'm sort of going to tease you. Like, why might that not be a good way to think about it? Think linear programming. What would be the analogous statement about linear programming?
Smallest unlimited vectors.
There you go. That's right. Peter's got it right. That is, I could write down linear programming as minimize Cx, Ax equal b, the smallest component of x has to be non-negative. But it turns out that thinking about it that way gains you nothing. We really need to think about LP and thinking about sort of separately each of these guys being non-negative. And likewise, turns out for semi-definite optimization. Okay, thank you. Okay. That is that. So now that I've written it down, is LP a special case? Is LP a special case of semi-definite programming? Okay. Len, what do you think?
Nothing comes to mind immediately.
You don't see that. Okay, so it turns out it is. Okay, so, and maybe you can help me figure that out. Okay, so there's several ways to do this. Let me suggest the worst way to do it. Okay, even it's the most straightforward. Sort of, if I take my LP and I sort of think of, well, I'm going to have my x be positive semi-definite. But if I really only want my variables, if I want to take an LP where my x, each component of x has to be non-negative, I could say, okay, this guy's got to be positive semi-definite, and all xij are equal to 0 if I is not equal to j. So that means the off diagonals of this matrix X are all 0. So I'm only really thinking diagonal matrices. And then a diagonal matrix being positive semi-definite is the same as?
All of the diagonal values being non-negative.
That's right. They're all non-negative. So, and then I can do that similarly. Like I could say minimize C dot X, where, again, C is just C1 through Cn with zeros everywhere else, etc. So then C dot X is just going to be C transpose X. Okay, do you see that? Does anybody not see that? Okay. Anybody not see that? All right, so that LP is a special case, but of course, you're going to want to solve an LP as an LP. Okay, you're not going to want to convert it to a semi-definite program. Okay? All right. So now let's look at some duality. This was the primal problem. So in order to get the dual problem, okay, I'm going to first need to know, so that this is really this constraint here, x positive semi-definite, is really x is in Sn by n plus, which is, again, the set of all x's that are symmetric and positive semi-definite. And then I asked you to prove in the homework that the dual of this cone is also the semi-definite cone. All right. So, oh, you know what? I don't have a proof of it. Yikes, I didn't do a proof of that in here. Uh-oh. Huh? I don't think I have a proof of it in this notes. Is that correct?
Halfway, like one way.
Yeah, I wanted to do the other way. Shoot. Uh-oh. That means I'm going to have to do this on the fly. Or you can help me. Okay, so I claim, right, that let's look at Sn by n plus its dual cone.
I have a question first.
Yes.
In the note, several times you use like k by k and mix it with vectors of length n.
So is that right? I mostly used k's.
Not here, but for the previous the problem sets, and also like for duality theory, you use K instead of.
So I purposely do these little things to keep you on your toes. So, no, I tell you why. Let me just, that I actually wrote these notes up, boy, about 8 years ago. Okay? And my thinking about SDP has changed since then, and I made a few modifications. But also my pedagogy about SDP has changed since then. Okay? And so it turns out that nowadays I like to use SK by K. All right? Do you want to know the reason? I'll tell you the reason. Okay? So the reason is that usually when we think of n, we think of that's the dimension. That's the dimension of what's that's the dimension where the action is taking place, as it were. Okay? But the dimension where the action is taking place is here is n times n plus 1 over 2. Okay? And so I prefer n to really refer to the dimension of the action, as not the size, not the number of rows or the number of columns of a matrix. So that was my thinking in that, and I apologize if that's caused you.
I think what was confusing is in the question it says, show that the dual of sk by k plus is equal to Sn by n.
Yeah.
Really? That's the kind of thing, like, you should bring me up for disciplinary charges for that. Where is that? That's in the additional homework?
And also the previous notes.
It's in the SDP notes?
No, it's not STP, that's duality theory. It's conic optimization part.
All right, so,
Everywhere it's mentioned up to this point is wrong.
Yeah.
I think.
Every time you have that sentence,
It's on page 52 of these.
all right, so of the SDP notes or the duality notes?
duality.
Page 52 of SDP notes. And where in the duality notes?
I think it's towards the end, and it's conic optimization.
Okay, and conic optimization, it's all wrong.
And also the additional exercises.
Yeah, and the additional exercises. Okay. All right, SK by, that's hilarious. I apologize. How many of you figured out what I must have meant? Okay. How many of you did this really ruin your weekend? Okay. There you go. All right. So, my apologies. All right, so let's see. Shoot, I have to do this on the fly. So, here we go. So, I'm going to use n by n here. All right. So, first thing I want to show you is that, oh man, actually this is not such an easy, yeah. All right, no, all right, so boy, this is the kind of thing I want to be able to refer to my notes in real time, not to have to think in real time. So let's see, so let's say, so first I claim that, notice that if y is positive semi-definite, then I want to show that x dot y is non-negative. So that's going to show us that, all right, my first claim is Sn by n plus is a subset of Sn by n plus star. So this says the original cone has to sit inside the dual cone. Okay, and then we're going to go the other way. Okay, so to prove this, I'll say, okay, well, let y be in the original cone. Okay? And then I need to show that for any x positive semi-definite, that y dot x is non-negative. Okay? And that's relatively easy. So let me just ask, Ashish, did you get this far? You didn't get, all right. So let me just go through this. All right, so watch. So I can write y as, I should try and be consistent with the notes here. Oh, I'm not going to be consistent with the notes. I'm just going to have to make this up as I go. So watch. I can write y as P transpose, right, where P is orthonormal and E is a diagonal vector, a diagonal matrix with the eigenvalues of y. Okay, and because it's positive semi-definite, that this diagonal matrix has what sign on the diagonal? Non-negative. And likewise, I can write x as, say, Q transpose, same story. Okay? So watch. So and I'm going to do this a little different. Now, maybe I'll do it the same. All right, so y dot x is just P transpose dot Q transpose. Okay? I'll tell you what we'll do here. I don't want you to write this down. I want you to look at it, and then I'll give you time to write it. I sort of promise. Okay? So this is the trace, okay, because we have the, let me just write this here, right? M, for any two matrices, M dot n is the trace of M transpose n. Okay? So this is the trace of this matrix transpose with this matrix, but this matrix is symmetric. And so this is just the trace of P transpose, Q transpose. Okay? This is the miracle of the trace. So working with the trace. But now this is the same as the trace of E P transpose, Q transpose, P. Why is that? What allowed me to quickly, without batting an eyelash, go from this row to this row? Yeah, remember you had to prove in the homework, trace of AB is the trace of BA. And so this is trace of P times this mess is the same as the trace of this mess times P. Okay. The other way I think of it when I actually do these proofs, ladies and gentlemen, is so long as I keep the relative order in here, I can just shift things. I can always take something from the left and put it over on the right, or vice versa. Okay, now what is this? So this is going to be, so now watch. Now I'm just going to put brackets here and say this is the trace of a diagonal matrix on the left times this. Now this is a positive semi-definite symmetric matrix. P transpose QD, Q transpose P. All right? I know that this is positive semi-definite and symmetric. And so what are the diagonal entries of this going to be? Right, those are going to be non-negative. And so this is going to be the sum of the EII, so I equals 1 to n, EII times this mess, II, which are going to be non-negative. Okay, sorry, this was PT, QD, QTP, which is a positive semi-definite matrix. All right, now you can write that down. Okay? So the first lesson, in fact, about semi-definite programming is that it ain't quite LP, and the proofs ain't quite LP-like. If I take two non-negative vectors, I know their dot product is going to be non-negative. That's like a half-a-line proof. Because, right, the sum of the products of non-negative numbers is non-negative. Well, it turns out the result extends that the dot product of two positive semi-definite matrices, okay, is going to be a non-negative number, but the proof was not quite so trivial. Mind you, nothing deep here. There's no separating hyperplane here. Okay? No separating hyperplane, but still it required a little bit of manipulation. Okay, so I proved that that's the first claim, which I've just proved. Now I want to prove the second claim. And so the next thing I need to show, okay, is that Sn by n plus star contains Sn by n plus. Okay. And now I'm going to say suppose not. First I'm going to wait. Is there anybody who needs more time? Are you all done? Okay. Anybody else writing this down? Okay. Claire, you look like you're too busy writing to put your hands up. Okay, good. All right. All right. Do you have the notes for today? Okay. All right. So now I claim suppose not. That is, suppose I have y that's in the dual cone, but y is not positive semi-definite, and I'm going to get a contradiction. Okay, so watch this. If y is not positive semi-definite, well, since y is in the dual cone, it's a symmetric matrix, and so y is actually equal to PD, what did I have? PEP transpose. PEP transpose, because it's symmetric, where E is the diagonal matrix of eigenvalues. But now what do I know about the signs of E? I've got some negative one. Okay? So pick your favorite number. Peter.
Peter's a good number.
No, pick your favorite number.
Okay, can I ask a question first?
No, you got to do the favorite number
Negative
first.
one.
No, I need a positive number.
Hi.
I need a. Ask your question.
How do we know that any matrix in the dual cone is symmetric?
We just define it that way.
Okay.
One way to think about it is, I'm going to go back to that earlier comment that I can. I need to define my space. So if the space is, no, my space is going to be dimension n times n plus 1 over 2. So it's going to be, everything that I'm going to be working with is going to correspond to symmetric matrices.
That makes sense.
Okay.
So,
right.
so one. Can I choose one?
Yes, you can choose one. Thank you. Okay. So PEP, so now suppose, for example, the first entry of this is negative. Okay. Let X be P. Peter, what is your last name? J, P transpose, where J is just the diagonal matrix with a 1 in the first component. Okay. Then clearly, defining X this way, X is positive semi-definite, right? Because it's P times a non-negative diagonal entry matrix times P transpose. Okay. But what is Y dot X? Yeah, watch. Well, let's just multiply it. So y dot x is going to be the trace of y transpose x, which is the trace of yx, because y is symmetric. Okay, and yx is going to be, here, don't write, just watch. Okay, sorry, y dot, E had a negative entry in the first entry. It had a negative, its first component was negative. Okay? And so I made J be a 1 here and 0 everywhere else, and defined X to be PJP transpose. Okay? And so Y times X is going to be PEP transpose, PJP transpose, which is just PEJP transpose, okay? Which is P times sort of basically some negative number here, and zeros everywhere else, P transpose. Trace of this, and that's a negative number. Now, why is that a negative number? Yeah. So Teo just, so one is I can just, so now I'm going to use that great property of the trace. Well, this is the trace of this negative number, P transpose P, just by moving my P over. Okay. P transpose P is what? That's the identity. And so this is just the trace of this negative number with all these zeros, which is less than 0. Who did that proof this way? Okay. Everybody on the left side of the room plus Alp. Okay. I wonder what that means. Okay. So with that in mind, right, see, these notes were written, I'm sorry, for a slightly different era, or a slightly different pedagogical approach, so that I just wrote down the dual. We didn't try and define it. But we know the semi-definite dual is going to be the maximum, according to our conic duality theory, it's going to be the maximum sum of the BI-YI, sum of the AI-YI plus S equals C, and S is in the dual cone. Right? But the dual cone is the same as the primal cone in this case. The cones are self-dual. So this is my semi-definite dual problem. Okay? Everybody with me? Karina, are you with me here? Okay, I'm just picking a face in the crowd, that's all. All right? Now, one can easily show, just as you've had to do in the homework or whatever, that the dual, that for general conic problems, the dual of the dual is the primal, or equivalent to the primal. And I could mix up all of these modes, just like linear programming. I could have some equations in here. I could actually have some linear inequalities in here, etc. Okay? In other words, and actually, if I have time, I may show you this, even though it's not in the notes. Usually these days now, when we talk about semi-definite programs, we actually sort of say, these are problems that have linear structure, except they have linear inequalities and semi-definite inequalities, either in the variables or in the constraints or somewhere. Okay, but it's all, semi-definite programming, in a sense, also subsumes linear programming. Okay. If this is my primal, let's just write Z star here, and V star equals here. Okay. I should point out, actually, sorry, before we talk about weak and strong duality, okay, that this is a convenient way to think about the problem. Because I could think of, actually, let me show you this. If I take a look at that same example that we had earlier, we'd look at the same example that we had earlier. My dual objective function is going to be sort of b1y1 plus b2y2, which is 11y1 plus 19y2. Okay. And then this sort of says I need a multiplier times the A1 matrix plus a multiplier times the A2 matrix plus a, sort of think of this as the slack matrix, equals the C matrix. And that this S has to be positive semi-definite. Well, if I rearrange this, this says I got to maximize 11y1 plus 19y2, and then if I just move everything around, this says, for example, 1 minus y1 minus 0y2 is in the first entry here, and each of the entries of c minus y1 a1 minus y2 a2 is a linear function of y1 and y2, and that this matrix has to be positive semi-definite. Okay? And one could think of graphing this in 2 dimensions. But of course, testing if a y1 and y2, I mean, this is a way to think about it. We've got a nice region here. In y1, y2 space, I know that's a convex region. So if I'm in y1 and y2, this is going to look something like this. Who knows what? It's going to be convex. Okay. And it's going to sit literally in R2. Okay. So it's say here, it's often easier to sort of see and work with the dual form, just as in linear programming. Okay? All right. So I have proposition 5.1 at the top of page 11, which states weak duality. But we actually have a nice proof of weak duality already. Okay. In fact, based on the fact that these two cones are self-dual, that the cone is self-dual, who could give me a two-line proof of weak duality? You can. Okay. I need a volunteer. Teo, thank you very much. Okay, so Teo, let me help you get started, okay? So watch. So suppose X is feasible for the primal, and suppose we'll say YS is feasible for the dual. Where are you going to go from there?
Can't you just take S dot X and say it must be related to the duality gap?
Yeah, but first we got to, right, so in fact, let's just watch. C dot X minus sum of the BI, YI, right? That's going to be primal objective minus dual objective. Okay, well, let's see. C is just sum of the YI, AI plus S dot X minus the sum of the YI, BI. Everybody with me? Nothing deep happening here, okay? But AI dot X is what? BI, right? So this is just the sum of the YI, BI plus S dot X minus the sum of the YI, BI, okay? These guys cancel, and so my duality gap is just my dot product of my two objects, okay? What do I know about the sign of this? Who just said that? Pamela? Say it louder.
It's greater or equal to 0.
It's greater than or equal to 0 because S was positive semi-definite and X is positive semi-definite. And so these guys are in self-dual. These guys, this is in one cone and this is in the dual cone. By definition, this is not negative. So that's weak duality. Okay. What about strong duality? So now here's where I'm a little embarrassed because my notes at the bottom of page 12, it sort of says, actually I'll just read this to you. Unlike the case of linear programming, we cannot assert that either the primal or the dual will attain its optima or that there will be no duality gap. One such regularity condition which ensures strong duality prevail is a version of the Slater condition summarized in the following theorem, which we will not prove, but we have already proved it. Right? So when we did conic duality, we said that if I have a point in the interior of my... What was the strong duality theorem for conic optimization? Who could state it to me with only making minor errors, as they stated? Okay. Somebody other than who had just volunteered. It was Teo had volunteered. You are Gordon?
Yeah.
Gordon.
So if a subgradient exists, and subgradient has to exist, so there's a Slater point.
Okay. So that was for Lagrange duality. Right? So Lagrange duality was based on there's a subgradient of the perturbation function. A pretty non-constructive mechanism. And then we showed, in fact, that a Slater point for the Lagrange primal, okay, guaranteed the existence of the subgradient. Okay. But then we studied conic duality, and we proved a theorem, in a sense, independent of all the other duality stuff. Who remembers what it is? We're just going around here. Okay, so Jan has his generals coming up, so he knows all of this stuff cold. All right, go for it.
If we have a stator point to the primal, then
For a primal conic problem.
conic.
So let me write down the primal conic problem, right? It was min Cx, Ax equal b, x in a cone. Okay? Who remembers what the dual is? I realize I know this stuff off the top of my head because I teach it. And I realize you might not know it off the top of your head, but you did know it a week ago, right? Who remembers what the dual of this problem is? Okay. Waleed.
Maximize B transpose U.
I'm going to write it with a Y,
Okay.
but you can keep saying it with a U if you want.
So A transpose U.
Okay?
Minus C or
Okay? Keep going.
plus S, okay. We'll see.
All right?
And then S belongs to K star.
Good. That's right. That's right. All right. So these were the and notice these are just special cases. Semi-definite programming of primal and dual are just are special cases of this. Okay? And then what did the strong duality for conic problems that we proved in class, independent of everything that we had done on Lagrange duality, is what? And Jason, you remember? Oh, you're looking it up. Good. That's good enough, actually.
If the primal problem has a slave point, then
And-
it's from duality.
So it's x naught is in the interior of K, and ax naught equals b, right? That was it. Okay. So that's a Slater point for the primal, meaning it satisfies my equations and it's in the interior of this cone. Okay. Now let me ask you this. What does it mean to be in the interior of this cone? Think. What would it mean for a matrix to be right? Peter's got it. Positive definite. Why? Because if x bar, think of it this way, right? If x bar is positive definite, okay, then you know what? It's going to stay positive definite for tiny changes in any of the coefficients. Okay? And so I now need, so a Slater point really for this problem is it's a feasible x that's positive definite. And likewise, a Slater point for the dual, I could sort of say it's a y and an s that's feasible, and s is positive definite. Okay? And so under those either of those two circumstances, right, if I have a, so now, all right, so now I've got to Gordon, and then, I'm sorry, I get confused. It's either high or high bow, and I think it's high. I got it right?
Yes.
Right, okay. I'm going to mess up everybody else. Okay, so high. If I have a Slater point for the primal, what do I know about, what does that imply? It implies no duality gap, right?
Yes.
And what else? You remember? You don't have to remember. That's okay.
Take a second shot at it.
Gordon again, right? You're the other Gordon.
No, I'm the only Gordon.
You're the only Gordon. Jason, Gordon. Okay.
Okay, yeah, the dual is optimal and attains.
And the dual attains. So let me give you a semi-definite program, by the way, that doesn't attain. Or can anybody think of one? Can anybody think of a semi-definite program that doesn't attain? Well, most of you don't know how to think about semi-definite programs yet, so I'll give you one. So here's a semi-definite program that doesn't attain. Min x. So x is a 2 by 2 semi-definite system. Okay. Is equal to and x positive semi-definite. Okay. I just invented this off the top of my head. How do I do that? Okay. Well, lest you sit in awe of my capability to just invent semi-definite programs, let me just tell you, I think to myself, okay, what is this condition saying, actually, about the entries of x? Huh? All right, so this off diagonal, so then, right, so x, think of it this way. X is this matrix here, and I've got x11, x12, x21, x22, but of course these are the same, right? And so this condition is just sort of saying x12 has to equal 1, right? Because it says this entry plus this entry of x have to equal 2, and they have to be identical. Okay, so that this just sort of says my matrix X is now limited to look like this. Okay, and I want to make x1 as small as possible. How small can I make x? Can I make x11 0? No, because if I make it 0, right, remember what we said earlier. If this is 0, these guys have to be 0, but they're 1s. So this can't be 0, but can it be arbitrarily small? Rachel, why?
Well, all it has to do is be positive, right? In
So-
order for x to remain positive.
So I got to be careful. I can make this epsilon, but now what is x22 going to have to be? Good. Karina's right. This has to be bigger than or equal to 1 over epsilon. Okay. So right, because for a 2 by 2 matrix, the condition that it be symmetric, positive, semi-definite is this is non-negative, this is non-negative, and the determinant is non-negative, which means this times this has to be bigger than or equal to this times this. So I need, this has to be at least 1 over epsilon. So I can make this arbitrarily small by making this arbitrarily big, but I never attain. So that this, in fact, equals 0. That's z star is 0. Sorry, z star is the minimum of this, which is 0. Okay, but the primal doesn't attain. Walid, you're in consternation over this.
I'm just wondering, does this really have an interior? Or is it like in one direction or in two directions?
Okay, so now, so just think now, does the primal have an interior? So the primal doesn't attain, but this has a Slater point, right? So the Slater point is, watch, the Slater point for the primal is easy. 5115. 511 pi. Okay. Right. This is a positive definite matrix. Okay. So I find a positive definite matrix that satisfies my equation so that there's no duality gap. So the primal doesn't attain, okay, and that's going to mean that the dual cannot have what? Pamela? Right, the dual can't have a Slater point. Okay? So if you, all right, so we're going to, the dual can't have a Slater point. Well, the dual, just work it out. I'm looking at the time. I don't have time to do it, but take the dual of this. Actually, all right, let's do it quickly. All right? So the dual is going to be, we're just going to put a multiplier y1 here. The dual is going to be maximized 2y1, and then the dual is going to be 0, 1, 1, 0, y1 plus s equals 1, 0, 0, 0. Okay? Why can't the dual have a Slater point? Oh, sorry, and s is positive semi-definite. Take a look at that dual and tell me what the only feasible solution is. So let's rewrite the dual this way. Watch. Yeah, y1's going to have to equal to 0. And in fact, that means s is going to be only positive semi-definite. But let's just watch. Let's rewrite this as this is 1 minus y1 minus y1 0 has to be positive semi-definite. That's my s is just 1 0 0 0 minus blah 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 times y1. Everybody with me here? Okay. So notice I can't get s to be positive definite here because I got a 0 here, so y1 is going to have to be 0. So the only feasible solution is y1 is 0 and s is 1, 0, 0, 0, which is not positive definite. So the dual has no Slater point. Okay? All right. We need to move along. So on page 13, let me just point out some facts to you. Okay? How many of you have had Professor Britsimus for a course? Okay. How many of you think he's smart? Forget it. Okay, you guys are just so. What? Oh, aha. Okay. All right. He's not smart. He's very smart. Okay. No. So Dmitry Britsimus is a very good friend of mine. We wrote a book together. I wrote all the good parts. So no, Dmitry came up to me, I think it was the summer of 92 or 93, and said, there's this new stuff called semi-definite programming. We really ought to learn this. And we both started to learn it, and he said, I bet there's a combinatorial algorithm for it, like the simplex method. I bet there's an analogy for a basic feasible solution. And I bet there's a finite algorithm for it. Okay. So turns out he was wrong about those things. Okay. So that is, semi-definite programming, on the one hand, it looks like it's almost LP. It is not a combinatorial. It doesn't have a component that's pure. It doesn't have a simplex method. Okay. And that has some ramifications. So watch this. Because if I give you a linear program, linear optimization problem with rational coefficients, the simplex method teaches us that there'll be a solution with rational coefficients. Right? In fact, I can bound the number of digits I need for things. That the solution, if I give you some reasonable input data, the solution isn't going to have that the ninth component of x is going to be, Avogadro's number, 6.23 times 10 to the 23rd. That's not going to happen. Okay? It can happen with semi-definite programming. Okay? So that semi-definite programming, it turns out, doesn't have convenient sort of finiteness about it. Okay? There is a simplex method for it, but it is not a finite method. All right? So I just want you to know that. All right, now what I'd like to do is show you some applications. Yes?
How does the sort of geometrical intuition of that then compare to that of the mountain?
So,
is there some deep reason why there's...
Yes, just think of it this way. Watch this. So Claire's got to ask a good question. All right, so you can think of it working somewhat like this. That if I have two equations, a1x equal b1, or say a1x less than or equal to b1, don't write this down, because I'm not exactly sure where I'm going with this. Okay? And a2x less than or equal to b2. Okay? These things, two linear inequalities imply another linear, or in a sense, watch. If x is less than or equal to y, and y is less than or equal to z, this is a linear relationship between x and y and z. It implies a linear relationship between x and z. Okay? Now watch what I can do with semi-definite programming. Okay? I can model easily that I can model y less than or equal to x squared. Okay? I can model this constraint. No, x squared less than or equal to y. Wait a minute. X. Which one do I want to do? Hold on. Yeah. Y less than or equal to x squared, x non-negative. Okay, so how do I do that? I just sort of say I want the matrix y1xx. Oh, that's y bigger than or equal to x squared. Okay? I don't even need x non-negative. So y bigger than or equal to x squared, notice I can model this way. Right? This says y is bigger than or equal to x squared. All right, if I can do that, and then I can also model, I got to get this right, x is bigger than or equal to z squared. Okay. Then I get I get this right? Yeah, y is bigger than or equal to x squared is bigger than or equal to z to the fourth. Okay, because this says x squared bigger than or equal to z to the fourth. Okay, so I can, in just 10 of these things, like this, I can get variables that sort of say one is bigger than the other raised to the 2 to the 10th power. Okay, and so everything can just literally blow up on me. All right, so that's the explanation. Is it that semi-definite inequalities somehow don't... Only linear inequalities have the property that linear inequalities only imply linear inequalities. Whereas this just sort of says quadratic inequalities can imply, you know, if I have 10 quadratic inequalities, it can imply inequalities with polynomials up to the power 2 to the 10th. Okay? It's polynomial, but very, very high degree. That's all. Okay. So now let me show you a couple of applications. Okay. How many of you have heard of the max cut problem? Okay. How many of you have heard of what's called the Goemans-Williamson result? Okay. All right. Andrew has. All right. So let me go over that with you. So this was Michel Goemans is a professor here in the math department, and so let me outline. Suppose I have a graph. Now, I'm not an expert at combinatorial optimization, so just don't ask me too many questions about this, okay? But just watch. I have a graph, okay? So I got a bunch of nodes here, and I got a bunch of arcs, undirected graph, and I put weights on each. I put non-negative weights. Wij, non-negative, is the weight on the arc from I to j. In particular, then, Wij equals Wji. The following is an NP-complete problem, which is divide the subsets of the nodes, divide the nodes into two subsets such that the arcs that cross that subset have maximum weight. That's called, so everything that crosses, say, from here to here, I sum up its weights, and that's maximized. Okay, that's called the max cut problem. I want to cut the nodes. I want to cut the nodes into two groups to maximize the weights of the arcs that cross from one group to the other. Alyssa.
What is NP-complete?
It's really hard. Okay, so just think of it this way. So the question was from a student named Alyssa who said, "What does NP-complete mean?" Okay, so that's the, huh? NP means non-deterministic polynomial. So let's put it this way. These are problems. So these are problems for which. So these are problems that have the following property: that we don't know of any well-guaranteed algorithm whose bound is not exponential in the natural size of the problem. The bound of the number of operations doesn't grow exponentially. Okay? And so that's the NP part. The NP-complete means is that it's a problem that if we could find a good algorithm for it that wasn't exponential in the dimension, then we'd have a good algorithm for every problem in that class. So that's what it means. Just think of it as it's just a hard problem. Okay, so I'm going to now formulate the max cut problem as a discrete optimization problem, and then I'm going to formulate it as almost a semi-definite program, and then I'm going to relax it to a semi-definite program, and then I'm going to state a result. Okay, so I can formulate the problem as follows. That is, I can think of, I will assign xi to be either 1 or minus 1 for each node I, and all those that are labeled 1 are in one group, and all those that are labeled minus 1 are in the other group. Everybody with me? And so then my problem is going to be maximize 1/4, and I'll explain where the fourth comes from in a moment, the sum over all ij, wij, 1 minus xi, xj. where xi times xj, xi is in 0, 1. All right, let's see why this is true. Oh, sorry, minus 1, 1. Okay. So notice if two nodes are both assigned a 1 or both assigned a minus 1, this product is going to be 1. So this is going to be 0. And so it's not counted. So that means the arcs that are in here aren't counted and the arcs that are in here are not counted. Okay? If they're assigned a different, if one is given a 1 and the other, if xi is given a 1 and xj is given a minus 1, this is going to evaluate to minus 1. So this is going to evaluate to 2. So I should divide by a half. Why do I divide by a fourth? Because I'm double counting. Okay? So this is the max cut problem. Okay? So what can I do to this problem? Well, watch. Now I'll define a matrix Y to be XX transpose. So this is an outer product matrix. So this just means Yij is just Xi times Xj. And so now my problem is maximize 1/4 sum of the Wij's. And I'll just write it minus sum over all ij, Wij, Yij. And I have the constraints y equals xx transpose. And the condition that xi, each of these x's is minus 1 or 1, what is that going to mean in terms of the diagonal of y? It's always going to be a 1, right? Because the diagonal here is going to be yii is going to be xi squared, which is always going to be 1. So I can write y equals xx transpose, and yii equals 1, I equals 1 to m, or 1 to n. Okay? So this also is a max cut problem. Okay? So now let me get it into a format that's almost an SDP. We're almost there. So this is maximize 1/4 the sum of the Wij's over all I and j. That's just data. And then I'm just going to write this as W dot y. Right? Sorry, this was, I need the fourth here. Right? That's just my inner product of W and y. And now I'm just going to write, I have the constraints that yii is my matrix. 1, I equals 1 to m. Okay, I got n of these inequalities. And the fact that y is xx transpose implies, so I'm just going to write y equals xx transpose for some x here. But also notice y has to be positive. If y is an outer product, y is positive semi-definite, right? Okay. So this is my max cut problem. Okay. I'm going to relax it. So this is max cut exactly. Okay. I'm going to relax it by just getting rid of this constraint. Now I have an SDP. I have a linear objective function of my matrix y. Y has to be positive semi-definite and satisfy some equations. And I'll call this relax. Jan.
At what point do you relax x equal minus 1 or plus 1?
Oh, I never relaxed that because that was implicit here. Right? The fact that yii has to equal, yii equals 1, if this constraint was still in it, that means xi squared has to equal to 1, which means xi is 1 or minus 1. So I never relaxed that. In a sense,
There's no more x's.
huh?
There's no more x's.
I don't need my x anymore, right? Because I got rid of this. But if I had left this in, it would imply that, in fact, that my x would satisfy xi is 1 or minus 1. One way I can think about this is, this says that y has to be a rank 1 matrix, and I'm relaxing that rank assumption. So we have just proved, okay, that relax is bigger than or equal to the value of the max cut. Okay, we just proved that by just literally crossing this out. Okay, so here's the amazing fact. Okay, and I got to get the number correct. The number is, what is it? 0.8786.
856.
87856. Thank you. 856 relax. And it turns out that this number is bigger than max cut, but not a lot bigger. Okay? Yeah. Which means if I solve the semi-definite program, and that's in the worst case. Okay, that's the worst case. It usually gets within like 3 or 4% of optimum. Okay, in numerical experiments. Okay, so it turns out what that means is this is a relaxation of the problem, but a pretty tight relaxation. This is independent of the dimension. Okay, and independent of the data. Okay, that I can always get essentially within 12% of optimum. Okay, worst case. Okay, by solving this problem. The proof of this is embarrassingly easy. It would take me about 15 minutes to do because it involves actually taking an expectation of a random variable, something that I barely know how to do. But it turns out the proof is well within your grasp and is not difficult. And in fact, the brilliance of this result won an exponential number of awards. Okay, appropriately so. Okay, because not only was it a very, very strong result. Okay, but it was simple. It was actually simple. I mean, the proof is not really germane to this course, but I'm just telling you the proof is like half a page, 3/4 of a page, something like that. And Michelle Gomans and David Williamson are sort of geniuses for coming up with something so simple. Okay, so this has opened up the door, by the way, to use semi-definite optimization to develop sort of strong relaxations of a lot of discrete optimization problems. All right. We will see on Thursday some more applications, and then we'll start to see how we're going to use interior point methods to solve semi-definite programs. But before we do, let me tease you. You're going to have to answer me one question now. What barrier should we use? What barrier function should we use to solve this problem? We're just going to take Cx minus theta times sum plus theta. What should I put here that I'm then going to want to shrink theta to 0? What did we use for linear programming? The logs, some of the logs of the variables, right? Some of the logs of the variables. What should I put here? Yeah, it turns out some of the logs of the eigenvalues. We don't want any of those eigenvalues to go to 0. The sum of the logs of the eigenvalues is just the log of the determinant. We're going to put up here log determinant of x. And you're going to think, oh man, I don't want to have to mess with this. But turns out this is an easy function to work with. We can write down formulas for all its derivatives just like that. I will see you on Thursday. Leave your homework. Oh, now, Andrew, do you have homeworks to hand back?
Yeah, I have a file of homeworks to hand back. One of them doesn't have a name, so if that one turns out to be yours, see me so I can figure out who you are and get credit for it. And give me your problem sets that you're handing in.
All right, why don't you leave your problem sets to hand in by Hamid.